Thanks everyone for coming. We're talking about some DNS magic with cloud-native tools and open source tools. Who in this room has ever experienced a DNS issue or outage? Yes, that's what I'm trying to find out. Okay, yeah. So I think we know what we're talking about, and we know that it's always DNS, right? My name is Studler. I'm here with Fabian Schulz. We're both DevOps engineers in Swisscom. Swisscom is Switzerland's major telco and IT services provider. And we're also kind of in a transition from traditional telco to tech company, which is why we're speaking at events, and we are trying to push forward with open source and all these topics. A few talks which could give you the context on what we're talking about here. This DNS, cloud-native DNS system is just a part of the overall story about telco to techco, but also about evolving GitOps and using the Kubernetes resource model. So DNS in 5G core, that's what we're talking about today. What are the characteristics? So the first one is it's private zones, mostly used in the mobile network. So that's 5G zones, namely in this 3GPP network.org domain. Then it's only moderate throughput, so it's not your normal internet resolver. We're talking about tens to hundreds of requests per second, so it's quite moderate in terms of throughput and resource requirements and so on. And the third one is quite important because it has to be low latency. That's a requirement with other DNS systems as well, but in this case we really need to place the DNS server close to the consumer. The consumer in this case is the 5G core. The reason for this is that it's heavily affecting the overall network performance, which is why if we want to optimize the network performance, we need to optimize DNS latency. This brings us to a few requirements when we talk about DNS. So first of all, it's supposed to be geo-redundant, so we need to deploy it across multiple Kubernetes clusters, which should make it HA, so we cannot go with singletons. That also means that we should not share a management plane, so we shouldn't create single points of failures by clustering things. So we really decided not to have a shared management or control plane. The second cluster of topics is automation. We decided that it should be fully GitOps driven and fully automated, so no manual interaction, and it should be based on the Kubernetes API, basically integrating into the Kubernetes ecosystem using external DNS. We're going to explain what external DNS is in a bit, but that's quite an important point because we really don't allow any create, update, delete operations outside the Kube API. Then we have two additional requirements. One is proximity to consumer. That's because of the latency topic, but also because of the complexity of the system. The more hops you have, the more probability you have of failure. So we cannot allow a SaaS solution. And the last requirement is support of advanced DNS features. So we shouldn't just allow A and C name record creation, but also we need to support more advanced DNS features like SRV records or NAPTR. These are used in SIP phone calls and so on, so that's some mobile network magic. So this is basically the set of features that we need for our DNS system, and I'm going to show you the architecture now. Please don't panic, don't leave the room just yet. We're going to break it down for you, or at least we're trying to do that. What you see here is a multi-cluster setup with two clusters. The slides will be uploaded anyway, so you can dig into that later on. So we have a top cluster, a bottom cluster. All the blue boxes are DNS consumers. All the yellow boxes are basically DNS servers or DNS daemons. Could be forwarders, could be authoritative servers. And then for the arrows, We have blue arrows, which are queries. We have yellow arrows, which are DNS forwardings. And then we have API calls. The red arrows are Kube API calls. And the green arrows are API calls to our DNS backend. Now let's zoom in. We split it by half. We focus on one cluster, and we start with the DNS cluster in-cluster service discovery within the Kubernetes ecosystem. So usually you would have your Kubernetes DNS service, which is based on CoreDNS. In some cases, you can also deploy the node cache, which is based on CoreDNS as well. The node cache is completely optional. We have it here for completeness. We use it in the 5G core. In the demo resources, it's not there, but in the end, it doesn't matter too much. So the way this works is you have your pod, which will ask for some kind of service that it knows that it wants to try to reach. Eventually, this request will reach the Kubernetes API. It will reach the Kubernetes DNS, which will check the Kubernetes API. If there is a service of that name, if there is a service, it will return the IP. That's a very simple process. It's using the Kubernetes plugin within CoreDNS, and it's using the Kubernetes API as its backend. So there is no other state than the Kube API. The feature is clear. It's in-cluster service discovery. And what it does not include, it's not exposed outside of the Kubernetes API or outside of the Kubernetes cluster. And you cannot create any custom resource records, such as TXT, SRV, and so on. If you're interested in more resources, there's quite some extensive documentation on kubernetes.io. It's great. If you're interested in digging into it, please follow these links. So now that we know that we cannot use this Kubernetes DNS for anything like SRV records or anything additional, we need to look into an authoritative server that we can use for our 5G core DNS. We came up with 3 shortlisted technical solutions. First one is CoreDNS, which is the same tech stack we use in Kubernetes. So that's how we thought we could share the know-how and so on. Then we look at PowerDNS because it's one of the most established DNS servers in the open source community. And the last one is basically a SaaS-based solution like Route 53. These requirements are a subset of the 6 requirements you've seen earlier. I go through them quickly. So external DNS support, that's the automation we're talking about later, is given with all of them. We can create A and C name records with all of them, so that's fine. When we look at more advanced records such as NAPTR or others, we can see in CoreDNS that's not supported. That's given by how CoreDNS integrates into external DNS. So there's no easy fix for that. We would probably need to write the plugin, a separate plugin for PowerDNS, and the SaaS solution that was fixed in a GitHub PR. So that's fine now. And when we look at the proximity to the consumer, obviously the SaaS solution is out. So that's how we found our winner. We are going forward with PowerDNS, and we're going to show you later how it actually works. So we started with the Kubernetes DNS in our architecture. We're going to zoom out a bit now. You can now see a single cluster which contains on the upper right side, you can see external DNS and PowerDNS. So basically, we are using external DNS as our syncer from the Kube API to the PowerDNS backend. So external DNS reads from the Kubernetes API. It reads static resources, which are called DNS endpoints, CRs, on the Kube API. These are basically YAML representations of DNS resource records. And we read dynamic A records from the Kube API. There it's important to know that the IP address is dynamically assigned by maybe the service load balancer, and ExternalDNS reads this dynamic IP from the Kube API. Then ExternalDNS will update the DNS backend, which in this case is PowerDNS. It basically writes, it bulk writes to the PowerDNS API. So that's how ExternalDNS works on a very high level. If we look at the state or how ExternalDNS and Kubernetes manage state, we can see in this case that's a dynamic assignment. So we have, for instance, we have a service of type load balancer. You can see there is an annotation that basically defines the DNS name. So that's all defined in Git, but you can see there's no IP defined in Git. When we sync that using Flux or Argo, when we sync that to the cluster, it will be a copy with an additional status field, which is the actual IP. That's how Kubernetes assigns IPs to load balancers. What ExternalDNS does now, it reads this IP and it syncs it to the DNS backend. So that's basically the dynamic allocation process of ExternalDNS. I showed the same picture for the static assignment. There it's way simpler because we basically define, as I said, it's a YAML representation of resource records that we define in Git. It will be synced to the cluster. ExternalDNS will read it and create records in the DNS backend. In this case, we have one A record and two MX records. So that's on a very high level how ExternalDNS works. Fabian will now show you a live demo of this very example. It's not the exact same values, but it should show how it works.
Yep. So let's come to the demo part. So all the demo is available on GitHub, so you can also try it out yourself. In there, so let's start with the demo. So here I have locally a Colima running, so just a VM and a local kind cluster. And in this kind cluster, we can have a look now what's running. So here on the right, you can see GitHub. You can see our page. We have my notes. So what we're going to have a look at now. So first, we see what's running. So we have ExternalDNS running and PowerDNS running. So the two you see here. And now, let me show you, for example, a service. So we have here a simple service. You can see this is just a deployment, an Nginx deployment, and to it a service. And here you can see the annotation we have, which is the domain name we want to give it, and there's no IP. So let's apply this service. Yeah. Dash. All right. So you can see the service, the pod being created. And if we look at the logs of ExternalDNS, we can see that it constantly looks at the Kube API. It saw, oh, there's a new record. It called the create, and now that means it called the PowerDNS API and created the entry. So now we can go check this out. So here I just have a short execute. So I do a dig in a pod. I dig for the Nginx 5GC domain, and here you can see I pass where the request should go to. So if I list the services, you can see this is our PowerDNS cluster IP. So you can see the 12, so I ask it, and I get the corresponding IP. And of course, this also works with the other type, which Joel showed, which is the DNS endpoint. So here I have a DNS endpoint. So let's apply the DNS endpoint. Again, if we go back to the pods and look at the log of ExternalDNS, we can see that it just created the endpoint. And now we can, like before, just simply query for the endpoint. So the domain is endpoint 1, and we get the response. All right, so this is already the first demo. Let me just start the second demo and then go back to the slides. So in the background, they can prepare. So now, what have you seen? So you've seen the left side, how this works, and the right side. So now how do we connect this? So for this, we first deploy another CoreDNS. This is our forwarder. So I call this a forwarder. This is deployed in our DNS namespace. Next, we'll configure the Kubernetes DNS to forward all the traffic to our forwarder. So of course, first it resolves the Kubernetes local ones, and then it forwards it to our forwarder. Our forwarder then does the triage. So all the requests that are for our domain, the 5gc.3gp.org, are forwarded to our PowerDNS, and all the other requests are forwarded to the internet. Maybe you also saw that there's a load balancer IP on our forwarder. So this is because we have some external consumers. So those are consumers that are not in the cluster. They also need to fetch DNS records, and they call the forwarder from externally. So now in the second demo, I would like to show you how this forwarding works. So let's come back to the demo. I switch here to the second part. What I want to show you first is the config map. So how is CoreDNS configured by config maps? So this is the config map of our forwarder. And if you have a look, you can see that we forward our 5gc.3gp.network.org traffic to our PowerDNS instance. It's the same PowerDNS instance as before. And if we have a look at the kube system, the config maps there. So here, this is the Kubernetes CoreDNS config map. You can see that first the traffic gets forwarded to the cluster local one, gets forwarded to Kubernetes. And afterwards, we forward all the rest to our 1096.0.11. So this is now our forwarder. We can go have a look at the service in the DNS namespace. We can see this is the 10.0.11. So it forwards it to our forwarder. And what does it mean now, what that changes? So basically what changes is that now when I do the request, I can just remove this PowerDNS and I get the response. And here again, also for the Nginx, I can remove it and I get a response. So this shows that we are here in a pod and the forwarding works and I get the response from our PowerDNS. So this is already the second demo, which is very short. Let me prepare the third demo. Where am I? Oh. Make demo 3. All right. Let's go back to the thing. So what do we have now? We have, bless you. Now we have one cluster. So this is our cluster. You see at the top it says Bern. So this is our Bern cluster. Now let's add a second cluster, which is in Zurich. So we have two clusters, Bern and Zurich. There's exactly the same things now deployed in the Zurich cluster. And what I want to note here is there's two PowerDNS deployments. They're completely separated, and each one has their own database. So there's no shared database. There's nothing complicated. It's just twice the same thing. Each one has their own PowerDNS and their own database. So now how do we kind of sync the databases or make sure that all the entries are in both clusters? So for that, we first deploy a second external DNS in the Bern cluster. This second external DNS watches the resources of the Bern cluster and then calls the API of the Zurich cluster. So now we have everything that is in the Bern cluster also available in the authoritative server, the PowerDNS of Zurich. Of course, we also want to do this the other way around. So there's also a second external DNS in Zurich calling the API in Bern. And this now gives us the following image. Now we should have all the information available in both clusters. So we want to utilize this now because now we just have it both there, but somehow we want to utilize it. So we need to add some forwarding, some fallbacks. So the first fallback is in the forwarder in Bern. We add a fallback to the PowerDNS in Zurich. That means if the PowerDNS in Zurich in Bern is not available, it will call the one in Zurich. We will do this the other way around as well. So the forwarder in Zurich will call the PowerDNS in Bern if the one in Zurich is not available. So now we remove the single point of failure of the PowerDNS. There could still be an issue with our forwarder. So that's why we also add a fallback to the Kubernetes DNS, where we call the forwarder of the other cluster. And we also add a fallback to the internet So this is, for example, in case something is completely wrong and all our both DNS namespaces, something is wrong and nothing works, we still want to be able to access the internet because I mean, DNS is still important if you want to debug something or download some images to debug something. We do the same thing the other way around. So the Kubernetes DNS has a fallback to the forwarder of the other cluster and to the internet. So this gives us then the final picture, which Joel started with. I hope it's a bit more clear now. So let's come to the third demo. So it's also the last demo, the multi-cluster demo. Let's see if it's ready. So for that, I'll start another K9S window. Let me open Firefox here. All right. So now you always need to pay attention to where I apply the stuff to which cluster. So it's two local kind clusters. You can see the top is Bern, at the bottom is Zurich. So the first thing I just want to show is that what's different now. So let's look at the deployments. You can see now there's the two external DNS deployments. There's an external DNS Bern and Zurich in the Bern cluster and the Bern and Zurich in the Zurich cluster because they write to both PowerDNS. I can quickly show you just that it works with the calling the service. So this is the Nginx service that we deployed here in Bern. You can see it's not in Zurich. Here in the context, I guess most of you know, you can select to which cluster you call the Kube API. So I call it in the bottom Zurich cluster, and I get the response. So this means you see that it's working. Now let's look up this. All right, now I want to show, of course, that it also works the other way around. So for this, I have another DNS endpoint, just a sample DNS endpoint here. We will apply this endpoint to the Zurich cluster, so the bottom cluster. If we look at external DNS, we can now see that if I go into external DNS, it created the Demo2 endpoint in the Bern one and in the Zurich one as well. So let's look up now this endpoint. So you can see now I did a dig in the Bern cluster of the endpoint, which I applied in the Zurich cluster, and I get the response. So this now proves that it works in both ways. The data is the same. So now that everything works, I want to try to show the resilience. So what I'm going to do is I scale down the PowerDNS deployment to 0 replicas in the Bern cluster. So you can see now that there's no PowerDNS in the Bern cluster. But the requests, if I do the request I did before, for example, endpoint 2, I get a response. And of course, we can also do that with the Nginx. So its own, so the Nginx, you remember, is the one we deployed in the Bern cluster. There's no PowerDNS, but it's still working. So this shows that this works. What's also nice is that everything is still working. So also we can also apply new things. So for example, I have another endpoint, endpoint 3, which I add to the Bern cluster where PowerDNS is down, but still we will have the external DNS of the Zurich cluster, which will fetch this. It will create it, and then we can look it up. So I can now do a lookup, and we have this endpoint 3, which is also available. So the next thing I'm going to want to do is scale down also CoreDNS. So now we also scale down CoreDNS here. If I go back to our image, so right now what we did before is we went from the forwarder to the PowerDNS down here, and now we go from, now this forwarder is also broken, so which means we should use the fallback route from this one to the forwarder down here. So let's do a lookup, and this, of course, this still works. And just to show you that, yeah, you can actually still break it, of course. So if I also scale down the forwarder, for example, in the Zurich cluster, if now I do the same request, I don't get a response, just to show that it's actually a live demo. And also now I can show at the same time that if I query for Google, for example, it takes 2 seconds because we have the fallback, like it waits 2 seconds to see if it gets a response from someone, and it didn't, but I still got the IP of Google. And what's of course also nice, if everything is done in a GitOps ways and it's constantly reconciling, is that if I scale something back up, for example, the forwarder, as soon as it's available again, it will sync all the resources again, and everything is back as normal. There's no cleanup or nothing to do. Yes, so this is the end of the third demo. And with that, I will hand back to Joël.
Yeah, thank you. Thank you for this impressive demo. You even broke things, so that's good. So I want to talk about limitations for a bit, because this system has a few limitations that are important to keep in mind. First of all, the way we built it is self-dependent, so we deploy the Kubernetes service on the same cluster where we consume it. The easiest way to mitigate that is by deploying dedicated clusters for DNS. Then we intentionally limited ourselves to use Kubernetes resources only. That's a design decision we took. So we won't allow it to use the PowerDNS API directly. You always have to go through Kubernetes and through GitOps. And the last one is the most important one, because I think it's crucial to keep in mind. We think that external DNS itself is not really supporting service discovery in the way we think it could, or it could if you rely on service discovery. I want to dig into that because it's really important. So first of all, it's interval based. So you define an interval to sync. So you will always have a delay, like this clicker. So the interval you configure will define the delay of the resources appearing in the backend. The second one is there are no health checks. So if you think of service discovery done in console, where you can basically define your health checks, that's not existing in this system. So you cannot rely on external DNS for app readiness, basically. Then the next one is multi-cluster round robin. So imagine you have an app that is spreading across multiple clusters, and you would like to use the same DNS names for this app. This is not possible. So also in our example, we can only have one, or each A record is owned by one source cluster, basically. So we cannot use DNS for round robin routing across clusters. And the last one is just important to keep in mind that if we lose an entire cluster in this scenario that Fabian showed, the entries will not get revoked because external DNS will probably also be offline. So there you need a tight monitoring and some additional automation. That's the limitations, but let's look at what we've achieved. So first requirement was geo-redundancy. That's given by spreading across multiple clusters. The second one was minimal amount of single points of failures, or reduce single points of failures. That's given by using a distributed control plane and by cross-cluster forwarding. Distributed control plane as in multiple instances. As Fabian has shown, we use only one, we use one database per cluster and not a shared or synced database. Then it's fully automated by using GitOps and external DNS, and it's integrated into Kubernetes. Everything is 100% Kubernetes resources. It's close to the consumer because we're using our on-prem deployment, and we support all or most or all records that we know of as of today, like NAPTR, SRV, and TXT records. So we think it's quite a solid system for our use case. If you're interested in checking it out, the resources are on GitHub behind this QR code. And with that, thank you very much for being here. Thanks for listening, and please enjoy the rest of the conference. I think we still have 5-10 minutes for questions. So if there's anything, please. Yeah.
Why is this not baked into Kubernetes basics?
Yeah, good
question.
good question.
Repeat the question.
Yeah, the question is why is it not baked in Kubernetes itself? I cannot answer for the Kubernetes maintainers, but I think eventually it will be a topic if you talk about cross-cluster reachability or service mesh. That, I mean, parts of this is also topics that service meshes try to solve, I think. But I don't know, to be honest. Kubernetes is focused on Kubernetes, which is only, it's focused on the inner part. And even when you talk about external connectivity, even the load balancer is not part of Kubernetes itself. It's something that the cloud provider brings, right? And so I imagine that was the reasoning behind it. But I don't know. Yeah. There was another question?
Yeah. Did you, so I'm guessing now external DNS is access to the PowerDNS and the other cluster. Did you ever consider flipping it around and letting external DNS read from the other Kubernetes API server instead? And if so, why did you go with the solution you chose?
Yeah. Yes, we did consider it. I don't know the exact reasons why we didn't go for that, but one simple thing that comes to mind is cross-cluster API access is usually more work to manage because you need to manage credentials or API tokens. But it's the same the other way around. But the PowerDNS integration is not automatic, basically. Yeah. Do you?
No.
Do you know? Yeah. Yes, please.
One question I have is like this cross data center Kubernetes cluster stretching problem. So we looked at that as well, actually from Bern to Frauenfeld. And we figured out that actually due to like physical limitations and speed of light and you know, like the timeouts that etcd requires or like the latency it requires, it's pretty much physically impossible. So you said you didn't want it because of the single point of failure, but have you actually also you know, looked at that or possibly?
So I mean, yeah. So the question is about the stretching of clusters. So the claim is that stretching an etcd cluster across geo-regions, I would say, is almost physically impossible because of latency. And if we considered that still. So I think it's two aspects. So yeah, for us it's really the way 5G core is deployed, it's single clusters in separate data centers. So that was basically these were the boundary conditions that we needed to build on. As for the cluster or etcd spreading across regions or locations, I think Switzerland is pretty much considered as a metro region at most because it's super small if you compare it to the US where this technology mostly comes from. So we use spread clusters. I think Bern, Zurich. That share an etcd control plane. So I think it's possible, but there will be limitations at some point, yes. Does that answer the question?
Yeah, for sure.
Okay, cool. Are there any other questions? Yes, please.
What do you use to expose the forwarder to the external customers or consumers?
So it's what we use to expose the CoreDNS forwarders to external consumers. Currently, it's based on load balancer services and backed in our distribution. It's backed by MetLLB. Also on the demo, yeah. There's one more. Yep.
You said that you wanted to have as least hops as possible in the entire setup. Now you got like 3 or 4 DNS servers in the entire setup. Did you check the latency?
The end-to-end latency, we didn't measure it yet. So sorry, the question was about a minimal amount of hops, and yet we have so many DNS servers in the chain. Fair question, I think. We didn't check the end-to-end latency, but since we're using the node local DNS cache, it doesn't matter too much. I think so. The way we tackled latency is mostly with the DNS cache, which helps us a lot because it's only affecting, I don't know, it's affecting way less queries compared to no caching, right? And the other thing is the amount of hops, which was more a problem in terms of the farther away the service is, the higher the chance that something breaks in this path. And if you rely on an external provider, even it gets even worse. Yeah. There was one more question from that area. Yeah.
Yeah, just the second one. Is there something specific to like 5G? Are there like specific scenarios where it would hit your system, or is it just a high available DNS server, or like just from the whole? Is there something 5G specific in there, other than like record types or something?
Yeah. So the question is if there is something 5G specific in this DNS system. I would say no, except for some design decisions that we showed. Otherwise, I would say no. There is nothing specific. As mentioned, it's not high throughput. It's mostly. So it's an internal DNS service that is only used by the 5G core component. So it's not exposed to users or to cell phones. So it's really only internally used. Yeah. All right. Thanks again. If you have more questions, please come up front. Thank you and enjoy the rest.